Hi, I'm Rohan. I'm an undergrad at Carnegie Mellon, and today I'm going to be talking about my solo author work at EACL 2023, Syntax-Guided Neural Module Distillation to Probe Compositionality in Sentence Embeddings. Though that title is a mouthful, I'm really just interested in the degree to which syntax serves as a causal structure for semantic composition. Richard Montague extensively studied this problem in the 1970s and 80s, and his view can be summarized as syntax is an algebra, semantics is an algebra, and meaning is a homomorphism between them. In other words, Montague views syntax as the input to semantics, where we can take a sentence, construct its syntactic parse, so for example, what John loves Mary, and then map this syntax parse into a semantic parse that leverages Montague's lambda calculus. So for example, we can take the word love and say that it takes a subject and an object, and then we feed the object into it, Mary, and then we feed the subject into it, John, following the syntactic parse, and now we have a semantic representation that comes out the top. In other words, the Montagovian view is that syntax is the causal structure of semantic composition at the symbolic level. But in deep learning, we no longer use these symbolic models of semantics. Instead, semantic composition is captured vectorially via embeddings. So our question now becomes whether syntax is the causal structure of vectorial semantic composition. To study this, we introduce SynNaMoN, or Syntactic Neural Module Nets. To construct a SynNaMoN, we take a sentence's syntax tree, for example, the rabbit sleeps, and we take each constituent in the tree and convert it into a module. These neural modules were introduced by Jacob Andreas in 2016 to study problems in visual question answering, but we adapt them specifically for the syntax case. So you can see how this noun phrase that goes to a determiner phrase and a noun in the syntax tree gets mapped to a module that takes an input of 1536, which is the concatenated versions, the concatenation of both the determiner and nouns embedding inputs. So we pass in each of the words individual embeddings, we pass them up through the SynNaMoN, and out the top we get a sentence embedding that has been guided by the syntactic structure of the sentence. The internal architecture of these syntax modules is non-trivial. How expressive should a single composition be? Probably somewhere between a simple addition of the vectors and like an entire transformer. So we just heuristically pick a few architectures to see how they perform. But future work should definitely explore the geometric expressivity required for semantic composition on a single level. For example, a determiner noun composition should be relatively simple, whereas something like adjective noun composition could be a lot more complicated and require more complex geometry to capture. So the three type of architectures that we use are this linear, nonlinear, which includes a linear layer passed through a ReLU, and then the double, which is nonlinear passed through another linear layer. To actually learn the parameters for these module nets, we take a distillation setup where we use a sentence embedding transformer to generate an embedding for each individual sentence. And then we generate the SynNaMoN, the actual module the module architecture for an individual sentence by using the sentence parse. Then we input the individual word embeddings for each of the words in the sentence into the SynNaMoN, and then we get a sentence embedding out the top of the module net. Then, now that we have this ground truth sentence embedding from the transformer, as well as an embedding that we generated via the SynNaMoN, we can use, we can simply compute the loss between those and backpropagate only into the SynNaMoN. So it's sort of like a distillation setup where the transformer's knowledge about sentence embedding that is learned distributionally without any inductive bias about syntax is then distilled into the module net via this training process. So there's sort of two views of how to interpret this distillation behavior. If you assume that syntax structure semantics as like classical linguists and like Montagovians would, then distillability measures whether the sentence embedding model is effectively capturing composition. Whereas on the other hand, if you take a more contemporary neural view, if you assume that sentence embeddings do effectively capture composition, and you think BERT or like sentence BERT is a great model of like sentential representations, then distillability measures whether syntax actually does structure semantics, which you might see as too far of a leap taken by the Montagovians. So let's look at some results very quickly. We run some experiments on BERT, MPNet, GTR, which are a slew of sentence embedding transformers, and we test them on our various internal module architectures, so linear, nonlinear, double. One thing to note is that adding the double doesn't significantly improve performance over linear, so perhaps composition is largely effectively captured by simple linear transformations. We also find that GTRT5XL performs the best in the sense that it has the highest distillability to these SynNaMoNs, which suggests that perhaps it has a higher degree of internal compositionality. So why might GTRT5 embeddings be more compositional? It might have something to do with the retrieval bottleneck that they introduced in GTR training that might be reflected in the mind. It's widely conjectured in cognitive science that compositionality has something to do with bottlenecks in the mind that force us to construct highly productive systems for generalizing to a wide corpus of data from just a small number of symbols and rules. So this representational bottleneck might induce more compositional representations and encourage their sentence embeddings to be more compositional in GTRT5. Also on an empirical note, we fixed our hyperparameters based off of the BERT training curve, but distillability scores could be improved slightly further with some tuning. Finally, one interesting anecdotal experiment is on our determiner noun phrase, our determiner noun module, which generalizes to the X plus noun syntactic categories intuitively, in the sense that determiners and adjectives are on this spectrum in the way that they combine with nouns, and quantifiers are somewhere in between. So you have words like some dogs, many dogs, and in some ways those are similar to saying the dog or a dog, but in some ways they're similar to saying black dogs or big dogs. But they're semantically in between, and we find that our determiner noun module generalizes in this continuous behavior depending on how similar or different the X's syntactic category is. So some concluding remarks. We proposed a method for testing whether syntactic structure can causally model semantic embeddings, and we explored some different views of how to interpret our experiments. We showed that GTRT5 broadly performs well, and this might have something to do with its representational bottleneck. We then suggested that composition is largely linear, since adding that extra layer didn't improve performance, improve distillability significantly. And we then showed how individual syntax modules, like our determiner phrase module, generalizes in the expected manner according to linguistic intuition. To draw a connection to classical Indian work in semantics and syntax, this is Shalakanatha Mishra's theory of sentential meaning, where he describes how individual contextual meanings for words, non-contextual meanings for words are first recalled by the words, after which linguistic rules are applied, sort of like constructing the SynNaMoN, and that results in the construction of vyakti, the independent individual sentence meaning. So in closing, there's a lot of empirical work left to do, but there's also a lot of room left for drawing connections to classical work, both in the Indian tradition as well as the analytical philosophy tradition. That's about it. Thank you.